One of the misconceptions about capacitors is that they store charge. This is clearly not the case because charge is always zero in total on a capacitor. But they can do work. So, for example, a capacitor can be used to light a light bulb. That means they must be able to store energy. In this lesson video, we're going to look into energy with a capacitor. Before doing that, we're going to go back and we're going to think about charged plates with a uniform field. There's a potential difference across the plates, V. Let's put a positive charge between the plates. Actually, no, let's put it right by the positive plate. So now the charged particle is going to want to move over to the negative plate. That means the electric field is doing work. W equals Fd, and hopefully you remember, we can also write this as W equals QV. If the particle was an electron and so Q equals E, we'd have W equals EV and the definition of the electron volt. Anyway, W equals QV. On a graph, let's start with a certain voltage but no charge. After the charge moves, we have the same voltage, and now we've got a value of charge, Q. I could shade this. And the area underneath here equals Q times V. So the area under the graph is QV, which is the work done in moving charge Q through PdV. If I move more charge, voltage stays the same, but charge increases. Making the area bigger, more work has been done. Now, instead of a battery, let's think about a capacitor in a circuit. The big difference here is that at the start, the potential difference across the capacitor is zero. Charge is also zero. If we increase the PD across the capacitor, PD increases and charge increases. On a graph, voltage on Y, charge on X. We start at the origin and both voltage and charge increase. I've drawn a straight line there. How do I know it's a straight line? Have a think about it. Well, the capacitance is defined as C equals Q over V. So that means V equals 1 over C times Q. Since capacitance is constant, that means V is proportional to Q. So now in this graph, the area under the graph is still telling us the work done. So that means that for charging a capacitor, W equals half QV. In a test, some of you are going to get that equation wrong. Please don't. If we increase the voltage a bit more, the charge will increase and the work done will be the area bounded here. Now there's one more pretty interesting result to do with capacitors. Let's say you have a capacitor storing 100 joules of energy. A single capacitor, like this, 100 joules of energy. If we connect it to a second capacitor, what will the total energy stored by the capacitors be? Yeah, what do you think? Okay, you may be right, but let's work it out to make sure. The first capacitor is fully charged, so W1 equals half QV. Let's change it to have two identical capacitors in parallel, and the charge spreads across the plates, which means that in this configuration, W2 equals a half Q over 2 V. And that is equal to half of W1. So half of the energy has disappeared. Is that really possible? Well, yes, it is. Let's consider something more familiar, water. We've got some water in a container here, and it has gravitational potential energy. The center of mass of that water is here, so taking the base as our reference, the water has Eg equals mgh. Now, if I open the valve, the water will redistribute itself to look like this. And now the center of mass is lower. The water has less gravitational potential energy. So where has the energy gone? Well, this is a physical system, so we can imagine, well, it's gone into kinetic, but then the water stopped moving, so it's carried on moving, the energy has rather, to somewhere else. And as usual, it's going to thermal energy. As the water moves, it rubs the sides of the container, particles interact, blah, 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 etc. It's quite complicated, but that's where the energy ends up as heat. In a capacitor, the energy will also dissipate through resistance heating. Why it's always a half of the energy that goes to resistance heating is pretty tough to show. You need to work with calculus and integrals, and I'm not going to do that. Now you might be thinking, yeah, but let's just go to low resistance wiring. Some of us have heard of superconductors, no resistance. Well, the problem with that is it just means the current will be really high. And that's going to give you electromagnetic energy being given off, just like an aerial. Got a current flowing, you're going to create a magnetic field, all that sort of thing. So half the energy is always lost. The main thing is, with the water, you can see it's true. The maths tells us it's true. It is true. Half the energy is lost. So in this lesson video, we've looked at two quite unintuitive things about capacitors. The energy stored in a capacitor is equal to half Q times V. And if we think about allowing the capacitor to discharge into another parallel capacitor, we lose half of the energy.